Hello, and welcome to this presentation, Understanding De-embedding. In this presentation, we'll provide a general introduction to the basic concepts behind fixture compensation and de-embedding in network analyzer measurements. This presentation assumes a general familiarity with network analyzers, including S-parameters and calibration methods. If you're not familiar with these concepts, or if you'd like a quick refresher, you might want to watch the presentations Understanding S-parameters and Understanding VNA Calibration Basics before beginning this presentation. As you should already know, the device under test, or DUT, analyzed or measured by a vector network analyzer is usually a network made up of one or more ports, each of which can pass, absorb, and/or reflect radio frequency energy. The VNA injects RF into one port and then measures the RF reflected back from that port, as well as the RF emerging from any other ports. These measured quantities are usually expressed in the form of so-called S-parameters, which are complex, frequency-dependent values. Generally speaking, there are two different kinds of DUTs. Many DUTs have coaxial connectors, such as N or SMA-type connectors. But sometimes, DUTs are embedded within a structure or a fixture, for example, on a printed circuit board. Measuring connectorized DUTs, that is, DUTs with coaxial connectors or terminations, is relatively straightforward. We simply use standard, preferably high-quality RF cables to connect to the ports of the VNA. We can remove the influence of these cables by calibrating at the DUT ends of the cables. This moves the reference or calibration plane to the ports on the DUT. This calibration is normally performed by attaching various calibration standards, such as a short, an open, etc., to the DUT ends of the coax as necessary. This is a common procedure in network analyzer measurements, and the methodology is fairly standard for all types of coaxial terminated devices. So what do we do if we can't directly connect our VNA to the DUT? For example, when our DUT is embedded in a structure or a fixture. One solution would be to somehow calibrate at the connection point between the DUT and the fixture, shown here as red dots. But this is not always possible or practical. There are, however, various methods that can be used to remove the effects of the fixture, and this is sometimes referred to as fixture compensation. So why is fixture compensation important? Clearly, we need some way of connecting the coaxial VNA ports to the device under test, even when the device under test is not connectorized. And as you should already know, calibration is critical for accurate VNA measurements. So it should be clear why we need a methodology or procedure that can compensate for or calibrate out the effects of the fixture. This need for fixture compensation is especially true at higher frequencies, and high frequencies are quite common in many modern applications. As frequency increases, wavelength decreases, and non-ideal behavior becomes more noticeable or more pronounced. For these reasons, accurate and consistent fixture compensation has become essential as applications move to these higher frequencies. There are four main approaches to fixture compensation: port extension or port offset, direct compensation, fixture calibration, and different types of de-embedding. In the remainder of this presentation, we'll examine and explain each of these different methodologies. We'll start with something called port extension or port offset. The reason this methodology is called port extension is that we assume the test fixture is perfectly matched and that it behaves like an ideal transmission line. The fixture is treated like an extension of the VNA cable, with a defined delay and a defined amount of loss. The amount of delay and loss introduced by these extensions may be manually entered by the user, or they may be automatically measured and determined by the VNA. This is done by placing an open, short, or both at the DUT connection points. Port extension is a standard feature on most VNAs. It's relatively easy to configure, but accuracy is somewhat limited due to the fact that real-world effects, like reflections, crosstalk, etc., are not considered in this methodology. The measurement setup for the direct compensation approach is similar to port extension, but unlike port extension, the direct compensation methodology doesn't assume that the fixture behaves like an ideal transmission line. Therefore, direct compensation measures the frequency-dependent transmission characteristics of the fixture, and then uses this information to compensate for the fixture. the DUT ends of the fixture are terminated with an open, short, or both, and best results are usually obtained when an open and a short are used. Note that, like port extension, direct compensation only works well at lower frequencies, that is, below a few gigahertz or so. Instead of modeling the fixture as an ideal or a non-ideal transmission line, we could also directly characterize the fixture, and this is often called fixture calibration. Rather than attaching a short and/or open at the DUT connection points, we perform a full calibration with a set of cal standards. This moves the calibration plane directly to the DUT inputs and allows us to calibrate out the fixture. Since we're actually measuring the fixture, fixture calibration is more accurate than the previously mentioned methodologies. Fixture calibration does, however, require characterized calibration standards, and these are often quite difficult to implement. One method of implementing these calibration standards is something called TRL calibration, where TRL stands for the calibration standards through, reflect, and line. These calibration standards are normally implemented in the form of so-called test coupons, which are specially prepared sections of printed circuit boards. Typically, TRL calibration uses 5 or 6 coupons of various types. Making measurements with multiple coupons creates a system of equations that can then be solved for the so-called error terms, similar to how this is done in the case of coaxial DUTs and cal standards. This methodology provides very accurate results if the coupons and the DUT have similar characteristic impedances. Although some people might refer to all methods of fixture compensation as de-embedding, in this presentation we're using the term de-embedding to describe fixture compensation by means of S-parameters. The way that this is done in de-embedding is by modeling the fixture as one or more additional networks, sometimes referred to as left and right, or lead in and lead out. The characteristics or S-parameters of these networks are known or can be determined. This does, of course, require additional measurements and calibration standards in order to create these mathematically modeled networks. Different mathematical algorithms can then be used to remove the effect of the fixtures from the measurements. In many cases, de-embedding produces the most accurate results for fixture compensation, but this often comes at the cost of additional complexity. In particular, it can be difficult to obtain the S-parameters for the fixtures or networks. Some fixture vendors may supply these parameters, but most often, users have to determine or derive these values themselves, especially when they're creating their own custom fixtures. One newer approach to de-embedding involves something called a 2x through. Conceptually, we start with a fixture containing a device under test, with both lead-in and lead-out traces. If we were to construct a single test coupon that is similar to the fixture plus the DUT in composition and dimensions, we could then subtract this coupon and be left with the DUT alone. In 2x through de-embedding, we use a fixture that has the same structure for the DUT and for the fixture alone. These are often constructed together as a single fixture containing both a DUT and a 2x through. The 2x through de-embedding procedure has 3 steps. First, we make a measurement of the 2x through. After this measurement is made, we then make a second measurement, this time with a DUT. Special software algorithms then derive the S-parameters used for de-embedding. De-embedding with a 2x through has several advantages. Although it's very similar to the TRL calibration we mentioned earlier, it requires fewer coupons and has similar or better accuracy than TRL. Fewer coupons also means 2x through de-embedding is faster and there are fewer opportunities for mistakes or error. This newer de-embedding methodology is well accepted by the industry, and in most cases the software algorithms can correct for impedance differences as well. So let's summarize what we've covered. A fixture is sometimes required in order to measure a DUT, for example in the case of a non-connectorized DUT. This fixture in turn can introduce some level of measurement error, especially at higher frequencies. We can reduce the level of error by using various methods of fixture compensation in order to remove the effects of the fixture, and there are a number of different ways of doing this, such as port extension, fixture calibration, TRL, etc. De-embedding refers to a process whereby we use S-parameters to create mathematical models of a fixture's frequency-dependent behavior, and 2x through de-embedding is one example of a modern de-embedding methodology that's become popular due to its speed, accuracy, and simplicity. This concludes our presentation, Understanding De-embedding. Thanks for watching.